Hello, today we're going to focus on Reactivity 3.2.9, which is all about oxidation for organic compounds, including with functional groups. So let's start in on combustion. And I'm going to use an example with just a hydrocarbon first. When you have combustion of a hydrocarbon, complete combustion will produce carbon dioxide and water. And so the oxygen is changing oxidation states from 0 to -2. The hydrogen stays at +1. The carbon here in carbon dioxide is +4. But you have kind of a weird situation with the carbon that's in the propane here. So in order to balance out the +8 charge, that means the carbons have to add up to -8. And there's 3 of them. So it's like -8/3 is an average of the 3, which is kind of interesting. But it is what it is. You can still see that it's clearly increasing as the reaction proceeds. So it's being oxidized. The carbon's being oxidized. The oxygen is, of course, being reduced. Its oxidation state goes down. Now that's for a complete combustion. If you have incomplete combustion, if there's like a limited oxygen supply, it might produce carbon monoxide instead of carbon dioxide, or it might produce just carbon with water. Either way, you're going to have different oxidation states formed because the carbon in carbon monoxide will be +2 compared to the -2 of oxygen, and the carbon by itself, of course, is 0. No matter what, it's still increasing. The carbon's still being oxidized, but it won't be quite to the extent as it was if it was a complete combustion. And you can also have combustion of functional group compounds, like alcohols. So let's say I've got propanol this time, like that. It can react with oxygen as well. And same thing, complete combustion will produce CO2 and H2O. Incomplete combustion could produce carbon monoxide or carbon. But just make sure, go back through and balance and be aware that the oxidation states of the carbon and oxygen will be changing. So let me remind you guys about the organic definitions of oxidation and reduction. Oxidation can mean losing hydrogens or gaining oxygens. Reduction can mean gaining hydrogen or losing oxygens. So that's really important to remember, especially when we're talking in here about the oxidation of alcohols. Now it's going to be a little bit different whether you have a primary alcohol, a secondary alcohol, or a tertiary alcohol. So something like primary alcohol, secondary alcohol, tertiary alcohol. And the reaction conditions, it will always happen in heat. And then the oxidizing agent that we're going to use is typically going to be something called acidified potassium dichromate. So I'm going to abbreviate acid and the K2Cr2O7. But you'll typically see it written out as acidified potassium dichromate. Okay, so when that happens, you can lose hydrogens from the alcohol. And if it's a primary alcohol, it's going to make an aldehyde. So 2 of those hydrogens will leave. And you're going to change that oxidizing agent from the dichromate ion into Cr3+ ions. You'll also have some potassium ions floating around. But the cool thing about this is that the potassium dichromate is like an orange or green color, orange or yellow color, whereas the Cr3+ is like a green color. So you can clearly see with a color change whether the reaction was successful or not. You'll see the same color changing happen with a secondary alcohol, but it's going to produce a ketone instead because the alcohol was in that middle position. So again, you'll lose 2 hydrogens and form the double bond O with the carbon. So that's a ketone. Tertiary alcohol, there's not really a way for you to remove the hydrogens and still satisfy the octet rule on all of the carbons and oxygens. So this will not result in any reaction, and you will not see any color change. Now, for primary alcohols, what's kind of cool is that you can continue to oxidize it. Because once it's an aldehyde, you can actually keep going and make it into a carboxylic acid. And so effectively you're adding another oxygen, you're adding another oxygen, so you're continuing the oxidation process. You still want to use heat and acidified potassium dichromate, but you also want to do reflux. And what reflux is kind of cool. It's usually start in like a round bottom flask. You have your reactants in there, but then there's this like tube, and it's like a double layered tube. So like this. And the outside layer has these like valves, and you can send water. You attach these with like to a sink, and you send water through the outside of the tube. So that's called a condenser. And as you are heating your reactants, they will start to evaporate, and some of the products will evaporate as well. And then the condenser, the cool water from the sink, is going to cool that down and condense it back into a liquid, so it will drip back down into your reaction chamber, and where it can heat up some more. And so this reflux setup allows it to, the aldehyde to continue to oxidize and become carboxylic acid. Now, if you absolutely do not want any of the acid present, then you might have to distill the aldehyde as you are doing the reaction, so that way you can collect the aldehyde before it goes too far. So that's really the difference then between primary, secondary, and tertiary. You will see color changes for primary and secondary. No color change for tertiary because there's no reaction that can happen. And then you can continue oxidation and get it to an acid if you reflux a primary alcohol to an aldehyde to get to that acid. Okay, so for this example, we're going to use oxidation numbers to show the difference in the extent of oxidation for the complete and incomplete combustion of pentane. So there's pentane, and combustion is always in oxygen. And I'm going to show you the complete and incomplete. So if it's complete, it will form carbon dioxide and water, where the carbon is changing to a +4. It could form carbon monoxide as one of the incomplete combustions, or just carbon, which is 0. But for the initial pentane, since each of the hydrogens is +1, the carbons have to be like -12/5 on average to get that to cancel out and equal, 0 overall for the compound. So no matter what, it's going from this negative value to either 0, +2, or +4. And this is the difference for complete versus incomplete combustion. And that usually depends on the amount of oxygen available for combustion reactions. Okay, so this one predicts the products of heating the following alcohols with acidified potassium dichromate solution and the color changes that would be observed. Butane 2-ol, so butane 2-ol, CH, that's a secondary alcohol. And then methanol, that's a primary alcohol. And they informed us that the product is collected by distillation. So the primary alcohol, we're not going to go all of the way to the acid because you are collecting it with distillation. You're not reflux. You're not doing reflux. So the methanol is going to form an aldehyde like that. And for the secondary alcohol, you're going to form a ketone like this. And since both of those reactions did happen, you will see a color change from that, like orange-yellow from the dichromate, potassium dichromate solution, into a green product. So you'll see it green, and that green is indicating that there was a reaction happening. So this links well with the nature of the functional group in a molecule affecting the physical properties. So I would talk about this in terms of the difference with distillation and reflux for the oxidation of those alcohols, specifically primary alcohols. The alcohol itself has hydrogen bonds. So you'll have the OH from the alcohol, and when that's oxidized and becomes an aldehyde, it's not going to have those hydrogen bonds anymore. So that's why we can distill it. It's going to evaporate faster at a lower temperature than the alcohol, and we can collect it through distillation so it doesn't oxidize further. If it did oxidize further, it would form the acid, and carboxylic acids also form hydrogen bonds, which have a higher boiling point, melting point, because of those stronger intermolecular forces. Okay, difference between combustion and oxidation of an alcohol. Combustion is going to be forming carbon dioxide and water, or if it's incomplete combustion, it could be carbon monoxide or just carbon. Whereas oxidation of an alcohol is going to be removing hydrogens or perhaps adding an oxygen. So removing hydrogens to form that aldehyde or ketone, or it could be adding an oxygen if you're going from the aldehyde to the acid, which is very different than what you're seeing in combustion, where you're actually breaking the bonds between the carbons. And then this also links to a higher level concept back in structure 3.1. Why is there a color change when an alcohol is oxidized by a transition element compound? And it's because of the oxidizing agent, the potassium dichromate, Cr2O7. And it's changing into Cr3+. And the oxidation state of the chromium in the dichromate ion is +6. So you're seeing a change in the oxidation state of chromium, which is going to change the color. And those transition element compounds tend to form colored complexes in water because the d orbital is able to split. It's very close in energy, but it's able to split into two kind of halves. And when the electron is able to move between the lower energy half and the higher energy half of the split d orbital, it's going to absorb certain colors of light to be able to make that transition, and then we are able to see the complementary color that is not absorbed. So because this is like a yellow color, it must be absorbing light in like the violet range, which is the complementary color, whereas the Cr+3 is a green color when we're looking at it, so it must be absorbing light in the red range.